In this example, I'd like to examine the torsion of a bar that's supported with a spring support with spring stiffness K, torsional spring stiffness K, and I'd like to examine how we can solve this using a potential energy method. So one thing to note is that in this system here, the rotation field for the bar has to be 0 at x equals 0. It's going to take on some value at x equals or z equals a, and between those 2 points it has to be linear because there's no distributed torque there. Likewise, all the way out to the end support, it also has to be linear because there's no distributed load between z equals a and z equals l. So z is our axial coordinate here. So we have a value here which we're going to go ahead and call theta a, that's unknown, and there's also a value here which we'll call theta L, and it's also an unknown. So let's first write down the potential energy for this system. So the total potential energy is going to be a function of theta A and theta L, and it's going to be composed of two parts: the stored energy in the rod, so it'll be an integral 0 to A of 1/2 GJ times the twist rate in the first part of the bar, which is theta A over A, plus the potential energy in the second part of the bar, integral A to L, 1/2 GJ theta L minus theta A divided by L minus A, and these are squared dz. So that's the stored energy in the rod. There's also stored elastic energy in the spring, so it'll be 1/2 K theta L squared. And we also have the potential load, so minus the applied load, A, times the rotation at that point, theta A. So we can go ahead and compute these integrals if we want. So the integrands are all constant, so it's relatively easy. So out of the first one we get 1/2 GJ over A theta A squared plus 1/2 GJ over L minus A theta L minus theta A squared plus 1/2 K theta L squared minus TA theta A. So for equilibrium, pi must be stationary, so that tells us that d pi d theta A has to equal 0. And if we go ahead and take those derivatives, we'll have GJ over A theta A minus GJ over L minus A theta L minus theta A, and then equals TA. So I've taken the derivative and moved TA to the other side, and then the other equilibrium equation comes from stationarity with respect to theta L, and that's going to imply that GJ over L minus A of theta L minus theta A plus K theta L equals 0. And so what I have here is a set of equations. These are the equilibrium equations for my system, and we can rewrite these, say, in a matrix form. Maybe it makes it a little bit clearer what's going on. GJ 1 over A plus 1 over L minus A minus GJ over L minus A minus GJ over L minus A, and then K plus GJ over L minus A. So you'll notice that the system matrix here is symmetric. Theta A theta L is equal to TA over 0. So written in matrix vector form, it's clear now that we have two equations in two unknowns, and they're also linear. So this can be easily solved, say, using Cramer's rule, and that will allow you to find out what the rotation at A is and the rotation at L is by solving these equations. And also, by virtue of this diagram over here, we also know then what the rotation is at any location z along the length of the bar.